Welcome to another podcast. In this episode, we're going to be taking a look at a comparison test for series. And the comparison test for series really comes from the integral test, because the idea here is that we know that if I look at the integral from 1 to infinity of the function 1 over x to the p dx, then from the integral test we know that that's related to the sum. K goes from 1 to infinity of 1 over k to the p, and the idea is we know the values for which this thing converges or diverges. In other words, we know that when p is equal to 1, this thing diverges. When p is greater than 1, we know that this converges. And when p is less than 1, we know that this diverges. Well, the same thing is true of the series, because when p is equal to 1, this certainly diverges. In fact, this is the harmonic series. When p is greater than 1, it would converge via the integral test. And when p is less than 1, it would diverge via the integral test. So if you remember what we called these back when we were doing improper integrals, these were called the p integrals. And we used those for comparisons to other integrals. We're going to do the same thing here, only now these are called p-series, and we're going to use them as the basis for our comparison with other series. And so the comparison test is almost identical. The comparison test for series is almost identical to the comparison test for integrals. That is, if you have two series, and you know that the values in the series are positive, and you know that one of them is less than the other one, then if the larger one, Bn, if the larger one is convergent, so if the larger one converges, then you know the smaller one also converges. Or if you know the smaller one diverges, then you also know that the larger one diverges. And so we're going to apply this comparison test and use these p-series as comparisons for determining, I have two sums here I want to look at, determining whether these sums converge or diverge. So starting with this first one, I want to use a trick to evaluate this one, or at least to tell whether it converges or diverges, and that is reindexing. If you remember, we talked about reindexing in a previous video as one of the properties that series have. And so if I look at this sum begins at 4 of the value k minus 1, and so you can see that if this were just 1 over k squared, 1 over k squared is p equal to 2, and p equal to 2 would be convergent. So p equal to 2 would be a convergent series. And so I'm going to make it 1 over k squared by adding 1 to the k inside the term, so I have to subtract 1 from k in the index. And so reindexing, this is the same as this sum. These are both the same. So going from there to there, I'm just using the property of reindexing to do that. And what I immediately notice is that this is the best way to write this is that this is strictly less than the sum k goes from 1 to infinity of 1 over k squared, and I know that this one converges because it's a p-series with p equal to 2. And so I know the larger one converges. This sum is larger than this one, so I know that this one must also converge. So I know that it converges by comparison. So converges by comparison. So that's just a simple trick, but it sort of lays the foundation for looking at a more difficult one. So the one that we have below, I'm looking at the sum n goes from 0 to infinity of 1 over 3 to the n plus n. And so taking a look at this, the best course of action here is to look at the sum n goes from 0 to infinity of 1 over 3 to the n plus n. And I notice that the n in the denominator this n right here, if I were to remove it, then that would end up giving me a p-series 1 over 3 to the n, where k would be 3 in this case. No, excuse me. It wouldn't be a p-series. It would be a p-series if you had 1 over n to the p. But I do notice it's 1 over 3 to the n, and that is a geometric series. So if I was to remove the n, I would be looking at the sum. N goes from 0 to infinity of 1 over 3 to the n. And the question is, removing that n, what does it do? Which of these is bigger? Should it be greater than or less than? Well, I'm removing an n from the denominator, so that's making this one larger than this one. And so the idea here, I actually said it right but wrote it backwards. Sorry about that. So this one is larger than the previous one. So removing the n makes the fraction larger, so 1 over 3n is larger than 1 over 3n plus n. So removing this turns into this. And the point that we want to make about this is this new sum that we have here, we should recognize as being a geometric sum. So this is geometric with r equal to 1/3 and a equal to 1, which means we actually don't need to determine whether it converges or diverges because we can actually sum that thing. We do know it's convergent. The actual sum is 1 over 1 minus 1/3, or 3/2. So the point is that this sum that we started with, it's less than 3/2. So this one converges by comparison to a geometric series with common ratio less than 1, which means it's a convergent series. So I wanted to show you two different examples of comparisons. One example of a comparison is a comparison to a p-series, and we've got all the information for p-series you could ever want right here. And then the other comparison that we can make is comparison to series we actually know sums of, and that's sort of limited. It's either telescoping sums, or the one that's more likely is a geometric sum. And so this is sort of how we would apply the comparison test for series, by comparing to known values, specifically p-series and geometric series. All right, thank you for watching.